Okay, so our next topic is Heapify. Well, the function or the operation of the Heapify, the goal is we want to maintain the heap property. And usually we want to do the Heapify when a specific location is wrong. It violates the heap property. Okay, so the Heapify assume that we are given a node which is the index I in the array, and then for the index I, we assume that it also has two children, the left and the right. Okay, and our goal, and for the left and the right children, we assume they are also the subheaps. Okay, and then the problem will be if the node I violates the heap property, and then how do we want to fix it? And when I'm saying I violates the heap property, how can it be? Well, if the I is smaller than any value of the left or the right, and then it violates the heap property, right? Then I have to fix it. So how do we fix it? Well, if the parent is smaller than any of the left and right, and then this value shouldn't really be the parent. So what do? We want to find the largest value between the left, the right, and then the parent, which is I, and then what value do we put as a parent? The largest one among the three, right? So this is what we want to do. We want to put the largest value among the three as a parent, and then we want to, if the parent is not qualified to be a parent, we have to flow it down either to the left or to the right. And then after we flow it down once, the job may not really be done. So we may have to float that value not qualified to be the parent probably all the way to the bottom or to a right place. Okay, so that is the Heapify. So let's see how we can do the Heapify. So for the Heapify, we grab the left child and the right child, and we assign them to L and R. Okay, and then we want to make sure that for the left child, it is smaller or equal to the heap size of the A, well, because we have to make sure there is really such a node in the heap. And if so, we want to check if the value of the left child is greater than the parent I. And if so, well, the largest will be L, and otherwise the largest is I. And for the right child, we want to do the same thing. We want to first check whether the right child is indeed a valid node in the heap. And if it is, and we want to check whether the right child is greater than the current largest. If the right child is even larger than the current largest, and then we want to update the current largest to R. But anyhow, we are recording the current largest to be really the largest value among the three, the I, the L, and the R, right? And then if the largest is not the parent, it's not I, and what do? We want to do a switch between the largest and the I, and after that, even though we move the parent down to a child, it's not guaranteed that the new location is the right place for the parent. So what do? We have to do another recursive Heapify for the parent value at the new location. So we do another max Heapify, and then this is still the array A, and the largest value is the new location of the parent I. Okay, so this is still a recursive process. So let's see this example. So when you see this heap, which value is wrong? We are doing a max heap, so do you see a value is not at the right place? Probably you see that it is 4, right? So it seems that 4 is the value at the wrong place. So what do? We want to specify a index 2 because index 2 is the value we want to fix. So how do we fix that? Index 2, we have two possible children, 14 and 7. So which value should be swapped with 4? The largest among the 3. So the parent 4, the 14, and 7. So the largest is 14, so we want to swap the 4 and 14. And after that, this 4 is at a new location, but is our work done? The answer is no, because the new location of the 4 is still not the right location. So what do we do? Well, what is the largest value among the 4 and then the 2 children? So 2, 4, and 8. The largest value is 8. So we do another swap. So after we do another swap, and now 4 is already a leaf. No left child, no right child. So, okay, 4, you stay here and you are finally at the right location. So you see, in this example, you will see even after one swap, it's not guaranteed that the new location is really the right location for that value. So we want to do a recursive heapify until this value is either at the right place or this value is already a leaf. Okay, so this is the Heapify, and for the Heapify, how do we analyze the time complexity? So let's see, how many times can we run the Heapify recursively? So what is the max number of the Heapify recursive calls we are able to run in the worst case? So what's the worst case? The worst case is we have a really small value at the root. And then what will happen? We have to pull the smallest value all the way from the root down to a bottom, right? So how far or how many swaps will be done? Think about that. That is the height, right? So what's the height? The height is log n. Okay, so remember I say, well, the height will be a very important factor we are going to use to analyze the algorithms, and this is example. So and if we have a heap, the size of the heap is n, and then we know the height will be log n, and then in the worst case of a heapify, we have to pull a small value all the way from the root down to the bottom, and then there will be a total of log n Heapify recursive calls. Okay, the next question. For the Heapify, let's see the algorithm again. So for the Heapify, for one Heapify, other than the recursive call, what do you see? They are all primitive steps other than the last line, right? So what do you feel? So for each of the Heapify, you may feel that if we exclude the recursive call, the rest of the Heapify is a linear algorithm. And how many times we are repeating this linear algorithm of the Heapify? We are repeating that for log n times. Okay, so this is the informal analysis of the Heapify, and we have a feeling that the Heapify should be a log n algorithm. But how do we really theoretically prove the Heapify is a log algorithm in a formal way? So, well, the first observation is fixing up the relation between I, L, and R once in one Heapify is a constant time, because there's no iteration and all the steps are primitive steps, right? And then, well, if the heap n, well, and if we are considering the case that if we are considering the worst case, and then what will be the worst case of the Heapify be? Well, before I answer this question, I want to show you this structure. For this structure, I'm assuming that we have a full triangle structure, and then that is really a full binary tree or complete binary tree. Okay, and then what's your observation? Well, if you assume that the triangle is the top n-1 level, all the nodes in the top n-1 level, and then in the bottom level, we divide the value of we divide the values on the bottom level to two parts, the left half and the right half. So one observation you are going to have is, well, the number of the nodes of those two triangles, they are definitely the same because it is a full binary tree structure, and then we are dividing the bottom level to two halves. So for those two triangles, there should be exactly the same number of the nodes. Okay? How about the number of the nodes in the triangle? So you can draw a complete tree structure on a complete binary tree structure on a sketch map, a sketch paper. And then what you will see is the number of the nodes in the triangle part, the top n-1 level, should be roughly the same to the number of the nodes in the rectangle. So you can draw a binary tree structure with the height of 3 or with the height of 4, and then you will see that. Okay, so for a complete binary tree structure using the height of 3, okay, using the height of 2, okay, so this means we have a total of 3 levels. And then in the top 2 levels, those will be the triangle. So how many nodes are there in the triangle? There are 1, 2, right? So 1, 2. Okay, so there are 3 values in the triangle. And then how many values are in each of the rectangle? So 1, 2. And after that, we have 4. But we are dividing the 4 into 2 halves. And then we have 2 values here, and 2 values here, and 3 values here, right? So that is for a heap using the height of 2. Okay, so you can do another one using the height of 3, and what you will see is, well, the number of the nodes in the triangle versus the number of the nodes in the rectangle, and you will always see, as long as it is a complete heap structure, and then the number of the nodes in those 3 parts, they are roughly the same. Okay, and then you will see, well, when we are doing the Heapify, we are pushing the value down to one side, and then are we reducing the size of the problem or the size of the sub-heap into 1/2? And the answer is not true. And how about we consider this case? For this case, we do have the triangle part, the top n level, sorry, the top n-1 level. And for the lowest level, we only have half on the left side, which is the left rectangle, but we don't have one on the right side. And then what you will see? And compare with the full heap structure, we only have 2/3 of the possible values. Okay, and then if we have a value to be heapified on the top, and we are pushing that to the left side, and then what do you have? You reduce the size of the problem, but you only reduce the size of the problem by 1/3. So this is the reason we have this Tn. So in the worst case, if we have the cost of the Heapify from the top all the way to the bottom as Tn, and in the worst case, we are pushing the value down to one side, and to be precise, to the left side. And then on the left side of the subtree or the subheap, we have roughly 2/3 of the data there. So that's why we are saying the Tn is smaller or equal to the T 2/3 of the n, and plus the constant time of doing this part to fix I, the relation of I, L, and R correctly. Okay, so if we start from this recursive definition of the Ln, and you will be able to prove that it is the case 2. And using the case 2 of the master theorem, and you will see the cost of the Heapify, even in the worst case, that is a log n algorithm. Okay, so well, in this part of the video, we talk about the Heapify, and then we see the examples, and we also do a informal and the formal analysis of the Heapify, and well, we use the master theorem, and we can prove the Heapify. Even in the worst case, it should be a log algorithm. Okay, so I will stop here. In the next video, I will talk about how we can start from the scratch and then build a heap. Okay, I will see you in the next video.